By the end of this lesson, you should be able to define work, W, as the product of an applied force, F, and displacement, S, of an object in the direction of the applied force. That is, W equals Fs. State that when work is done, energy is transferred from one object to another. Solve problems involving work. Who is doing work, the boy or the girl? What is meant by work, and how can we determine whether work is being done or not? The word work means many different things to us in our daily lives. We say that we work when we sweep the floor, or buy groceries, or drive a car. In physics, work is done when force acting upon an object causes a displacement. For example, pushing the trolley of books through a distance. How much work we do depends on how hard we push or how far we move the object. Work done on an object by an applied force is defined as the product of the component of the force along the direction of displacement and the magnitude of the displacement. Work equals force times displacement. W equals Fs. The SI unit of work is joule or Newton meter. The girl does work when she pushed the trolley of books. The boy does not do any work as the wall did not move though he applied a force on it. What will happen if the applied force is not in the direction of displacement but rather at an angle to it? If an applied force is not along the direction of motion, we can resolve it into components parallel to and perpendicular to the displacement. In this case, the object does not move in the direction of the force. Thus, if the force F makes an angle theta with the line of motion, then the component of force that contributes to the work is F cosine theta. The value of the work done if the force F equals 25 newtons, angle theta equals 45 degrees, and S equals 1.2 meters can be calculated as shown. Using the equation W equals F cosine theta times S, work done is 21.2 joules. Consider the example of a waiter carrying a plate of food. Let us calculate the work done by the waiter. How can we calculate work done by this waiter? The direction of the applied force and the displacement are not the same. They are perpendicular to each other. Since cosine 90 degree is 0, the work done is 0. The girl does work as there is a displacement as a result of application of force. In order for the girl to do the work, she needs energy. Where does her energy to do the work come from? Initially, the wheelbarrow was at rest as there was no force applied on it. There was no work done. When she pushes the wheelbarrow, a force is exerted on it. There is a change in its displacement and thus increase its kinetic energy. Where did the wheelbarrow get its kinetic energy? It came from the girl exerting the force, who used chemical energy stored in the food she ate to move the wheelbarrow. In other words, when the girl did work on the wheelbarrow, she transferred a certain amount of chemical energy stored in her to the wheelbarrow, causing its kinetic energy to increase. Energy is the ability to do work. Thus, work can also be defined as the transfer of energy from one object to another.
A box of weight 5 newtons is placed on an inclined plane which is making an angle theta with the horizontal. The box can slide down the inclined plane if the component weight of the box along the inclined plane is equal to or more than 2.5 newtons. Observe the work done by the force F, component of weight along the inclined plane, as the angle theta varies. What is the minimum value of the inclined plane? What is the minimum work done?